Hi, Brian. This is Helen.
Good day. How are you?
Hi, good. How are you?
So I'll get myself ready here. Where's my fake background? Hold on. All right. It's better.
Can you test if you can share the screen? The share screen, is the square screen works for you or something? There you go.
I see my videos going haywire, but can you see my screen?
Yes, yes, yes. Okay, the moderator just arrived. Moderator, my co-host. Il Yong, the moderator, just arrived.
Oh, my bad. Yeah, hey, Brian.
Nice to meet you.
Nice to meet you as well. Blur my background here. Cool. Yeah, I guess we should wait, or we should wait for people to join, I guess.
Yeah, people are joining. At least we're waiting for Dr. Depp. And people.
Yeah, I'm trying to remember my rules before I start. Don't talk with my hands and don't say So my two personal rules.
Yeah, it's definitely not easy on the second one, though.
Yeah, my brain and my mouth don't always work at the same speed. So we'll see how it goes.
It happens. It happens to everybody. So wait, Brian, are you in the Philippines right now?
Yes.
Okay.
No one ever guesses that. I think I'm always assumed to be in the US, maybe Europe. Nobody ever guesses the Philippines.
Well, I just saw in the Zoom link that the Philippines time zone was there. I'm like, who is in the like? It's probably Brian.
Yeah, when I schedule calls with people, I always have to put in there I'm GMT +8. My schedule looks weird, but it eventually works out. It's actually harder with North America, which is ironic since I'm an American myself, that some of the time zones are middle of the night, either middle of the night for me or middle of the night for you.
True. So
or in this case, you are talking to me in the future. I'm on Sunday morning, so I am time traveling and talking to you in the not so distant past.
True.
It's never funny, but I keep telling people that. Huh?
Are you in Manila right now?
No, I'm in the Cebu area, so the second largest city.
Oh, cool.
But there is a growing quantum ecosystem here, getting the government involved, some government funding, some hopefully some initial startups soon, hackathon later this year. So we're getting something going locally.
How long have you been living down there?
When did I get here? It's been 6 or 7 years.
6 or 7 years. That's crazy.
Yeah, time flies. And you're in Canada?
Yeah, I'm in Toronto right now.
Okay.
So, yeah, just, it's in that EST time zone.
You've got a bigger audience than I'm used to seeing.
Yeah.
That's a good thing. It's a good thing as long as people get an interest in dynamic circuits and preferably decide to start playing with them, then it's all good. If you can reach one person, it's worth it.
True. True. So, Helen, it is 7:31. Should I just start or?
Okay, sure. Let me hit the recording button.
Okay. Sure. Okay. Yeah, well, hey everyone. Thanks for joining. If you're based in North America, thanks for joining on a Saturday night at 7:30. Busy day, but you're here today hearing hot talk from Brian Siegelwax today. I don't know if you guys read he's a very good writer in the quantum space. I don't know if you guys follow Quantum Zeitgeist on LinkedIn. There's always some good content there. Also, he wrote the Choose Your Own Quantum Adventure, the personalized book. That's available on the website as well if you look at his bio. Brian obviously started his education at Rutgers, classic school. Yeah, it says that you did your MBA, but I guess you never finished it at the University of Phoenix, Brian?
Correct.
Yeah, but University of Phoenix, solid school. Yeah, he's currently an independent quantum algorithm designer and quantum machine learning researcher. And today he's going to be talking about dynamic quantum circuits, giving examples and talking about some of the advantages and disadvantages. So yeah, ladies and gentlemen, Brian Siegelwax.
Thank you very much. Let's make sure this is still working. All right, can you see that?
Yeah, I can see that.
And the slides are changing.
Yeah, it is.
I asked that because that's a mistake that's happened before. So thank you very much. Let's talk about dynamic quantum circuits. I am impressed that you pronounced my name correctly, Brian Siegelwax. The agenda for this talk is IBM Quantum Summit 2022, the IBM Practitioners Forum that was held the next day. I will give examples of dynamic circuits. We'll talk about the advantages and disadvantages of quantum circuits. And although this will be IBM-centric, there are other companies that support dynamic circuits as well, so I'll talk about a couple of those. And I'll be happy to answer any questions that you may have at the end. The answer to all of them is 42 anyway, so I don't know why anybody's going to ask, but I'll answer them anyway. The IBM Quantum Summit 2022 was held in November of last year, and IBM made a whole bunch of new announcements. The Osprey chip stole the show with its 433 qubits. But one of the announcements that they made was that they now support dynamic circuits on real hardware. The simulator has supported it since the very beginning, but when they made the announcement, 18 devices supported dynamic circuits. That's now down to 12 because they're always bringing new devices online. They're always retiring some old ones. So the moral of the story is if you want to experiment with dynamic circuits, take a look at what IBM or whatever company currently has available and see which of their devices support dynamic circuits. And what dynamic circuits do is they support real-time classical processing. What you would do now is you would design your circuit, you would wait in a queue for a quantum computer, you wait for the results to come back, you do some classical mid-processing, you wait in a queue again, you wait for the results to come back, you do some more classical mid-processing, you run out of breath, you wait in the queue, you wait for the results to come back, and you do some more classical mid-processing, and that sounds, that's very slow. Dynamic circuits move that classical processing next to the QPU, next to the processor. So you wait in a queue just one time. You do all of your classical mid-processing right there. You get the results back. You do your classical post-processing, and you're done. It's much, much faster. Dynamic circuits give us the opportunity to remove gates from our circuits. Every single qubit operation adds a chance for errors. Every multi-qubit operation introduces even more chances for errors. So the more gates that we can remove from our circuits, the less errors we will have. Dynamic circuits also enable feed-forward operations, which is the image on the right here, where we start with the U1 block. That is the circuit that we would normally design now. But we can add mid-circuit measurements. And then the U2 block going into the circuit, we don't know what that's going to be. We design it all out, but what that block is conditional to those mid-circuit measurements. We are dynamically extending the circuit during runtime, and then we can perform even more mid-circuit measurements. And with the U3 block, the same thing. That can be any number of qubits, any number of operations, and conditional to the measurements, we are dynamically extending the circuit further. Dynamic circuits give us the opportunity or more opportunities to trade circuit depth for circuit width. Generally speaking, the deeper your circuit, the more errors you'll have, the more noise you'll have. If you have more qubits available, you want to have a wider circuit and a more shallow circuit. And I'll show you an example of how dynamic circuits enable that. This image comes to you from this website that you can hopefully see here, which will also tell you everything, all the major announcements that were made at last year's Quantum Summit. Then when IBM made the news that hardware was now supporting dynamic circuits, at the time, what most people probably cared about was 3 free devices that supported dynamic circuits. And even though they've gone from 18 to 12 systems supporting dynamic circuits, they've gone from 3 to 6, the number of free devices that support dynamic circuits. So anyone can start playing with dynamic circuits right now. Preferably wait until I'm done talking, but you could start right now. But please wait. And this, by the way, is in the IBM Quantum portal. That's probably the easiest way to check. Take a look at the devices that you have available to you. And on the right side of the screen where it says OpenQASM 3, that's what you're looking for. If it says OpenQASM 3, it supports dynamic circuits. So removing gates allows us to remove potential errors from a circuit. This here is a 2-function Deutsch-Josa algorithm, which means it doesn't really do anything practical. But what we're looking at here is the middle qubit that has the X gate at the end. If this is the end of our circuit, or if it's the middle of the circuit, that X gate doesn't have to be there. We can implement that classically and prevent the errors that it might cause. So if there's a measurement that's coming right after that X gate, we take the X gate out, we measure a little bit sooner, and if we measure a 0, we can classically change that to a 1. If we measure a 1, we can classically change that to 0. That X gate does not have to be there. But removing one gate and removing a small chance of error is not going to impress anybody. So let's take a look at this circuit over here, which is just a Qiskit demonstration of visualizations. It's not meant to do anything important. And what we want to look at is the purple, the controlled swaps, also known as Fredkin gates. As I'm talking, I'm probably going to say them both interchangeably. I apologize. But anyway, we can take those out, the purple controlled swap Fredkin gates, and slide the measurements a little bit to the left so they're right after the Hadamards. And the controlled swap does not actually exist. It is composed of a number of single qubit and multi-qubit operations. They actually add quite a bit of circuit depth. And as you can see, we have 3 of them. So we have a lot of noise, a lot of chances for errors, and a lot of extra circuit depth. And we can completely take them out of there. And then what we can do classically, again, whether this is the end of the circuit or the middle of the circuit, we look at the value that came off of QB0, where the first control is, And if that value is a 1, then we can just classically swap the values that came off of QB2 and QB1. We can then look at the new value, or potentially new value at QB2. If that's a 1, we can classically swap the values on QB3 and QB4. And then we look at the value that came off of QB3. If that's now a 1, we can classically swap the values that came off of QB4 and QB0. And so we can do that all classically. And while we're at it, we might as well eliminate the X gates that are there as well. If we look at QB3, we start in the ground state of 0. We apply a Hadamard. We go to the plus state. We have an equal superposition, an equal probability of measuring 0 or 1. And then if we look at QB4, we apply an X gate. We go to the 1. We apply a Hadamard. We go to minus. We are again in equal superposition. We again have an equal probability of measuring 0 or 1. So for this circuit, the X gates make no difference whatsoever. And what we are left with are a bunch of Hadamards, a bunch of measurements, and some classical steps that follow. But what we really want to do is combine these. So we have the circuit on the left, which is a true quantum circuit that actually does something. And now imagine instead of the X gate, we have a controlled swap instead. So instead of a little chance for error, we have quite a few chances for error. We actually have more circuit depth with a controlled swap than you see in that entire circuit right there. That's how much depth a controlled swap adds to a circuit. But now that we have a deeper circuit and many more chances for errors, now we take that controlled swap out like we did with the X gate before. We slide to the left our measurements, and we perform those swaps. The conditional swap classically, if the condition is met, then we just swap the bits classically. It does not need to be done quantumly. Then dynamic circuits add opportunities to trade depth for width. I am not a fan of random circuits, but it's the best example and shows it fairly clearly that what we have here is a 4-qubit circuit that has a little bit of depth, doesn't look that deep until you look a little bit closer, and you'll see 4 swap operations, and each of those swaps at a minimum is composed of 3 noise-loving multi-qubit operations if those qubits are directly connected, and if they're not, it's even worse than that. So this circuit is actually much deeper than it appears, and if we have more qubits available, we can do something like the circuit on the right, where we use some ancilla qubits. You can see that the circuit is much more shallow. We can use mid-circuit measurements and classical operations to, in this case, perform some randomness, but it doesn't have to be random. But this is just a demonstration that we can take a relatively deep circuit. Well, it's not that deep, moderately deep, semi-deep circuit, and we can still remove some of that depth, reduce the time that the qubits need to maintain their coherence, remove a bunch of potential errors, and make the circuit more shallow, less noisy. The applications identified for dynamic circuits include quantum error correction, which is really the initial application. Syndrome bits are just the classical bits that you use now, but if you use them for error correction, just call them syndrome bits. And you perform some mid-circuit measurements, and then depending on the values of the syndrome bits, you perform the bit flip and phase flip corrections. Also, quantum simulation, I will show you an example of a dynamic variational quantum eigensolver a little bit later. Also, quantum machine learning, I will show you dynamic clustering and classification a little bit later. The Quantum Practitioners Forum was held the next day, and they took some of the announcements from Quantum Summit, and they just went into more detail. And one of the things that they announced was a staged pass manager. You design your circuit, you run the pass manager, even if you don't know that's what it's called. When you transpile your circuit, you're optimizing your circuit for the hardware that you're going to run it on. And the important part of that announcement is that they added a custom preset for error suppression. Imagine we have 2 qubits and one is being acted on dynamically. We initialize it, we use it, we measure, reset, reuse, measure, reset, reuse, measure, reset, reuse, and then we have another qubit that's not being acted on dynamically. It has to maintain its coherence while the other qubit is doing everything that it's doing. And while that qubit is doing, even if operations are being applied, it still has to maintain its coherence. So there is a custom preset for that qubit to try to suppress errors while the other qubit is being acted on dynamically. They also announced delay operations, which is kind of curious since they've been around for a while, but they announced them anyway. In the beginning, you designed your quantum circuit and you initialized your qubits and you did a bunch of stuff, and then the measurements came all the way at the end. So even if you're done with a certain qubit, that qubit would have to wait until all of the other qubits were done before the measurements could take place. Then when mid-circuit measurements were supported, that allowed the measurements to slide to the left. When your qubit is done, you can measure it immediately. It doesn't have to wait and wait for errors to possibly creep in. Delay operations work from the other end of the circuit. We initialize our qubits and we have a qubit we don't need just yet. We're doing things to other qubits first, and then we're going to do something to this qubit. We can delay when the actions happen on that qubit. And what we're doing then is from both sides, we are delaying when the operations start from one end. We are pulling in when the measurements happen from the other end. And we are trying to minimize the time that each qubit has to maintain its coherence. Again, the longer we use a qubit, the more noise is going to happen, the more errors are going to happen. So we want to minimize that, the time that each qubit needs to maintain its coherence. Then Mathematic used to be a separate library. It is now built into optimization level 3, which is the highest optimization setting for your circuits. But optimization level 3 does not support dynamic circuits. We can only use level 0, which is no optimization at all, or level 1, which is a little bit of optimization. And in principle, Mathematic should work on dynamic circuits. And if you don't know how Mathematic works, I will show you that on the next slide. Also, in principle, any conditional operation should work. Anything you would do now to build a circuit, you could also do dynamically. Although in practice, that's not the case. I've identified one operation that does not work. It's the initialized function. It only works at the beginning of the circuit, so you cannot use that conditionally. And what that means is if one operation does not work dynamically, then there might be some others as well. So keep that in mind as you're experimenting with dynamic circuits. In principle, anything should work. In practice, that might not be the case. Also, nested conditional statements are supported. If you don't know what that is, we take mid-circuit measurements and then conditional to those measurements. If this condition is met, then do something. A nested conditional statement is if a condition is met, then if another condition is met, then do something, or however many times you want to do that. But with dynamic circuits, you actually don't want to do that too many times, and I'll explain that later. Also, this is bolded and highlighted and in red for a very good reason. If you are new to Qiskit and you're just doing some experiments that are one and done, you run your experiment, you're done with it, you might not notice. But if you have a project that's going on for a while and you're continuing to add to it, you'll eventually notice that when Qiskit has a deprecation and migration policy, so every 3 to 6 months, everything's moving all around, which means because dynamic circuits are new and you need to upgrade to the latest Qiskit versions, when you do that upgrade, there's a very good chance that you're going to break your existing code. So the reason why I say that is you want to have a requirements file. Well, one or two options: have a requirements file so you can roll back to the versions that work, or you want to be prepared to troubleshoot your circuit and upgrade it to the latest version of Qiskit. One of the changes that you'll see initially is the provider is different. The way that you initialize the provider changes, so almost everything is guaranteed to require at least that upgrade. So again, this is just a cautionary statement before you upgrade and everything stops working. Requirements files so you can roll back and be prepared to upgrade anything that you are going to continue working with. Also, and this is just from IBM's perspective, there are 3 versions of dynamic circuits. There's the OpenQASM3 specification, which IBM contributes to, but they're not the only contributor. There are other organizations contributing to that as well, which means that if I am QABC company and I am a contributor, I am contributing to the specification what I want to see supported, and that means that other organizations might not be supporting those features. So if you see OpenQASM3 features that you would like to use, there's a chance that IBM does not support them yet, or there may also be features that IBM supports and nobody else does. Also, Qiskit and the hardware have 2 different levels of implementation. There are features that Qiskit has enabled that is not yet supported on IBM hardware. And interestingly, there are features that are supported on IBM hardware that is not yet supported by Qiskit. So the features that you want to use, whether the OpenQASM3 specification supports them or not, you need to make sure that the features you want to use are supported by both Qiskit and the hardware. And that's a little bit of trial and error still at this point, since it's relatively new. Also, the control systems have memory limits. So I asked the question at the forum, if I want to initialize a qubit, use it, measure, reset, reuse, measure, reset, reuse, measure, reset, reuse, how many times can I do that? And the short answer is we don't know, but there is a limit. So depending on how far you want to push dynamic circuits, there are limits which should continue to expand over time as the hardware is upgraded and as the software is upgraded. But keep that in mind that there are limits to how many times you can measure, reset, reuse, and how many conditional statements you can implement. Then I said I would explain Mathematic for anybody who doesn't know, and let's use the Manila device for an example. The device has 5 qubits. It does support dynamic circuits, and this is the connectivity diagram, how the qubits are connected. And imagine we want to entangle qubit 0 and qubit 4. We cannot do that because they are not directly connected. One of the things that IBM has always done that not everybody else does, but IBM has always done it, that we want to entangle qubit 0 and qubit 4. IBM will automatically add the swap. So for example, we swap qubit 4 and qubit 3. We swap the quantum states that are on quantum 4 and quantum 3. Then we swap 3 and 2. Then we swap 2 and 1. Excuse me. And then we can entangle qubit 0 and qubit 1. And when we get the results back, it'll still look like qubit 0 and qubit 4, when in fact we have measured, for example, qubit 0 and qubit 1. But the problem with that is all those swap operations, like I mentioned before, they add a ton of noise, a ton of opportunities for errors. And what Mathematic does, as the name implies, it maps, it looks at we want to entangle qubit 0 and qubit 4, and Mathematic says, well, gee, that's just silly. And I am going to map what you think is qubit 4 to the physical qubit 1. So you still think it's qubit 4 when you're designing your circuit, but Mathematic says, no, I'm going to map what you think is qubit 0 to the physical qubit 0, or whatever the best qubit is at the time, and what you think is qubit 4 to the physical qubit 1. So those qubits are connected from the outset. We entangle, we measure, all those swap gates are eliminated, all of that potential noise is prevented, and we measure, we get much cleaner results back. Then this is an example of quantum clustering and classification. This is actually old. This is several years old, demonstrating what we've always been able to do on the simulator. And again, the big news is that we can do things like this on real hardware. And excuse me, while I slowly die over here. If we look at the block sphere on the top left, what we have are 4 single qubit quantum states, and 2 of them are intentionally close together. Those are the red dots, and the other 2 are intentionally close together on the other side of the block sphere. Those are the blue dots, so that we have, for testing purposes, 2 obvious clusters. And that's what the left side of the circuit is doing. The left side is doing the clustering. Then on the right side of the circuit, we are introducing a new quantum state, and we want to classify that quantum state as either being closer to the red cluster or closer to the blue cluster. And I'll walk through this quickly if anybody's not sure what they're looking at. From left to right, surrounded by orange, OpenQASM2 has always supported subroutines. If you use Python, it's functions, it's the same thing. And when you looked at your circuit diagram, this nondescript rectangular block is how it used to look. They're now black, but this is how it used to look at the time that I was designing this. And that can consist of any number of operations. You can see, based on the size of it, at least 2 qubits that are involved. You can see the top qubit, the highest up qubit, and the lowest qubit, and the qubits in the middle may or may not be in use, but the rectangle just shows you at least the range of qubits that might be affected. And the depth of that could be 1, like you see on the diagram, or it could be 100 or 1,000, depending what you put into it. Then in red is a reset gate, which has always been supported on the simulator, and the simulator works the opposite of hardware. With hardware, the deeper the circuit, the more noise we have. If we can use more qubits and have a wider circuit, we want to do that, a wider, shallower circuit. For the simulator, it's exactly the opposite. Each additional qubit slows down the simulator tremendously. But on the other hand, the simulator doesn't care about depth at all. You can just keep piling on to the end of the circuit. You can just keep extending it. The simulator really doesn't care. This is a very deep circuit that we're looking at here once it's transpiled. So the reset gates, the purpose of those was to minimize the total number of qubits in use, to minimize the simulated runtime. Then in yellow, to the right of that, is a barrier operation, which I have historically used for explanation purposes, to divide up parts of the circuit so I can explain what each part of the circuit is doing. Generally speaking, you want to remove those from your circuit before you actually run it. But another thing that the barrier does, I mentioned the delay operation earlier, the barrier has always worked as a delay operation. So again, if you have qubits that are not in immediate use, you've always been able to apply the barrier to delay when operations begin on that qubit and to move it closer to the final measurements, and again, minimize the length of time that each qubit has to maintain its coherence. Then in green, those are the mid-circuit measurements, which in this case are determining the clusters, identifying the red cluster and the blue cluster. Then next to that in blue, although it looks like we have operations on our circuit, this is what makes it kind of dynamic. They're there, we can see them, but they don't necessarily execute. And below it in light blue, those are the conditional statements. So in green, we are taking measurements. We are measuring to syndrome bits, which again are no different than any other classical bits, just another name to make it interesting. And depending on the value of each syndrome bit, the operations in blue are executed if those conditions are met. So for example, if the 0th syndrome bit is 0, then execute this above, or if it's 1, execute this above. And everything you see at that point afterwards is conditional. Well, not everything. The resets and quantum states are not, but everything near the top of the circuit in red and blue is conditional to the mid-circuit measurements. And then all the way to the right are the final measurements, and that tells us the classification, the new quantum state. Does that classify? Is that probably part of the red cluster, or should it probably be classified as the blue cluster? And this is how it looks today, a little bit different. In yellow, we have a Hadamard gate. And I mentioned before, the controlled swap doesn't exist. It's composed of a number of operations. And the Hadamard gate also exists for our convenience, since it's a very common operation, when in fact it looks like what's on the right. It is composed of, and this is IBM specific, but it is composed of a number of operations. We then perform a mid-circuit measurement to the syndrome bit. And then in green, we are performing a conditional test. If we measure to 1, then let's apply an X gate to Q1. And then we perform our final measurement. So we will end up with either 0, 0 or 1, 1, which is normally a sign of entanglement, except in this case, there's no actual entanglement. We're kind of faking entanglement. But the important thing is that what's in yellow could be any number of qubits, any number of operations. What you see in green could be any number of qubits, any number of operations. And we're also not limited to just 2 measurements, as evidenced here by the dynamic variational quantum eigensolver. If you're not familiar with it, it's not terribly important. But the key thing here is when we look at VQE and everywhere you see measurements, what we're doing, so where you see efficient SU2, that's the initial circuit, the ansatz. It's a circuit with guessed initial parameters. But anyway, we take the mid-circuit measurements. And what we're doing now is we're waiting in a queue for real hardware. We're waiting for the results to come back. We're doing classical mid-processing. We're waiting in a queue again. We're waiting for the results to come back. And that is very, very slow. And this is part of the reason for Qiskit runtime, which is a service that you can use, another IBM service. And the point of runtime is to throw some hardware at your problem to speed up the classical processing and to also reduce the wait for the hardware. But you still have to wait for the hardware, do some classical processing, go back to the quantum processor, classical processor, quantum processor, easy for you to say, and keep bouncing back. So although it's much faster than, let's say, doing it on your laptop, it's still not a terribly fast process. But you can imagine if we could do this as a dynamic circuit, we wait for the hardware just one time. We have this ansatz to the left. We do the mid-circuit measurements. We do the classical processing right there next to the QPU, right next to the processor. We're updating the parameters as we go. We take the final measurements, we get the results back, we do our classical post-processing, and we're done. So in principle, much, much faster. Now, two things here, you would not actually want to design it quite like this because we're taking the first set of mid-circuit measurements and we're measuring to the syndrome register. And then the next set of mid-circuit measurements, we're measuring to the syndrome register, and we are overwriting the first set of mid-circuit measurements. So it all depends on what are the measurements that you want to be able to get out of the circuit. If you want all of the mid-circuit measurements, then each set of measurements needs its own classical register, which you can set up kind of sort of dynamically. There's a little trick to doing that programmatically, but you can do that. If you don't know how many registers you'll need, you can do that dynamically, programmatically. Or on the other hand, if you don't care about mid-circuit measurements, you can use just one classical register and measure everything to that, and then all you'll get at the end are the final measurements. So the important question is, does this work? And unfortunately, the answer is not quite. It's not, the hardware is not quite ready for this. The parameters that you would use, the variables that you need are currently limited to integers. And if you've used VQE, you'll know that that's not going to get you very far. So over time, we can hope that that will be expanded, and instead of just integers, we'll be able to use floats and be able to actually do this. But yeah, an integer-based VQE is not going to get you very far. But in principle, though, the concept of doing VQE in just one circuit should work. As evidenced by qSync, qSync 1 is a generative algorithm that composes music. qSync 2, there are actually 3 upgrades that are all kind of semi-finalized. They're being tested in actually generating music. And one of the new versions uses a dynamic circuit. And the hardware, like with dynamic VQE, the hardware is not quite ready to support it. But for the simulator, it absolutely does work. We do have a proof of concept where we start off with an initial set of rules. Let me take a step back here. So the initial version had a problem similar to VQE where we encode the rules onto a quantum computer. We wait for the results to come back, and that is the next note in our new composition, our new song. And we have to know what that next note is to know what the next set of rules are. And then we encode those rules on a quantum computer. We have to wait in a queue, wait for the results to come back to get the next note, so we know what the next rules are. And it could take, depending on queue time, several hours to compose a relatively small song, several hours. Now, with a simulated dynamic circuit, it is remarkably fast. And again, it does work in principle on the simulator. We encode the initial set of rules. The mid-circuit measurements are the next note in the composition. Then based on that, using conditional statements, and this is why it doesn't work, you need hundreds or even thousands of conditional statements, which again, the simulator doesn't care about. The control systems for real hardware absolutely does care. But on a simulator, no problem. Hundreds or even thousands of conditional statements. We encode the next set of rules, and then the next set of mid-circuit measurements is the next node in the sequence. And at the end, you have this super long bit string, and you parse that into each of the mid-circuit measurements and the final measurement. Then there is a decoding process to convert it back into the original binary representations of actual music. And then you play it and you listen to it, and it actually sounds pretty good. Then some new circuit design features, and all of these really have an asterisk next to them because there's, again, what's supported by the OpenQASM3 specification, what's actually been implemented in Qiskit and what's actually been implemented on hardware. But OpenQASM2 has subroutines which accept parameters, but dynamic circuits now support variables, but again, integers at the moment for IBM. And but still, instead of just being limited to subroutines, actual variables. And if-then statements have always been supported by the simulator, and now there is support for if-else statements. Then there are 4 while loops, and the closest we've had to that previously is whole register operations. If you have a data structure and you want to do something to the whole data structure, classically, you would loop through that. Quantumly, you don't need to because all of the qubits can be acted on at the same time. So we have a quantum register with 5,000 qubits, and we apply a Hadamard gate to the register. All 5,000 qubits have the Hadamard acted on at the same time. But dynamic circuits add 4 while loops. For purposes, again, we take mid-circuit measurements. Based on conditions, we can use 4 while loops to help dynamically extend our circuit. And they do not look like 4 while loops. They actually look more like if statements, but they're if statements implemented in such a way as to implement 4 while functionality. Also, classical computation is supported because how else would you do a dynamic VQE? You have the parameters. You need to be able to update those parameters next to the QPU, next to the processor, so you can update the parameters, extend the circuit dynamically, take more mid-circuit measurements, update the parameters, and so on to continue going. Also, conditional measurements are supported. So unlike the measurements we just looked at, we can take mid-circuit measurements and then conditional to what those measurements are, we can do additional measurements. So those measurements will not happen if those conditions are not met. And the difference between the measurements we just looked at, and conditional measurements is that the results are not retrievable at all. You still get the effect of it, but there's no way to assign that to a classical register and find out what happened. Only mid-circuit measurements and final measurements if they have their own dedicated classical registers. There are also other features like modifiers and timing, and again, it all comes down to what are you trying to implement it, you want to test it, and make sure the feature that you want to use is actually supported both in Qiskit or whatever you're using and on the hardware that you're using. If you need support, there is a dynamic circuits channel in Qiskit Slack, and ChatGPT isn't bad. It's interesting if you ask it, how do I implement dynamic variables, OpenQASM3 variables in Qiskit? It somehow knows, or it's guessing, even though it's not fully supported. It's not fully supported, but the code looks good. But anyway, ChatGPT can be a useful tool. How do I do this? How do I do that? Probably drawing from the OpenQASM3 specification and the Qiskit textbook, or however it does that, but it's another possible tool. Some other new features, new announcements, and this is, well, not all IBM specific, but features that are not directly related to dynamic circuits, but can be used with dynamic circuits, is circuit cutting. We have a circuit that is too large for any of the quantum computers that we have access to. So we find a point of weak entanglement and we cut the circuit there, and then we can run those sub-circuits on a number of quantum computers at the same time, and then we can classically knit the results back together as if we had a larger quantum computer than we actually do. Another way of using circuit knitting also is, imagine we want to simulate a molecule with different geometries. I won't get into what that is, but let's say a small one, lithium hydride, and we want to simulate or calculate the energy of 3 different geometries. We can run that on 3 different quantum computers at the same time, well, depending on Q times, and classically knit the results back together and do some classical post-processing, whatever we're doing with it. And an example of putting them together, IBM calls it entanglement forging, and there is a paper on this using a water molecule as an example. Simulating a water molecule requires 10 qubits, and if you're using the free devices, we only have 5 and 7. So what they came up with is we can split the circuit between spin up and spin down. We can do, and again, tying this back into dynamic circuits, let's say we're using dynamic VQE. So we can use dynamic VQE on one device for spin up. We can use dynamic VQE on another device for spin down, classically knit those results together and simulate a water molecule that requires a quantum computer that is otherwise larger than we have available. Then quantum serverless, I compared to Gmail, which I use. I have no idea where in the world my email servers are. I don't need to know. I don't particularly care. And that is IBM's roadmap for quantum computers. And they're not the only ones expressing an interest in doing this, where we focus on our circuits, much like if you're using the simulator. We don't care about qubit connectivity. We don't care about error rates or anything else. We are focused on our quantum circuits, and then quantum serverless will decide which quantum computers to use, quantum computer or quantum computers, and ideally handle all of those decisions. Just focus on your algorithm. And then IBM calls it middleware, that there's a recognition that we're not going to be developing algorithms in a vacuum. We are going to be developing applications of which quantum computation will only be a part of it. So imagine we are trying to develop some new materials and we have an application for that. And part of that application is we want to simulate some molecules, and that gets sent to quantum serverless, and we do some quantum computation over here. But now we want to do some visualizations, and we want to use GPUs for that. Let's say, for example, something involving IBM Watson. So the middleware handles that. That goes off to GPUs. Maybe we're doing some intensive data processing at some point. Maybe that goes to IBM Z. Doesn't really matter, but whatever the resources are, the idea is that IBM has, and not exclusive to IBM, but in this case, all of the cloud-based resources available. What does your application need? You focus on your application and what it needs to do. Don't worry about the infrastructure at all. Again, kind of like using Gmail. I send an email, I receive an email, no idea where in the world that's actually happening. A bit of a recap, the advantages and disadvantages of dynamic circuits. The advantages include opportunities to remove some gates from our circuits and to prevent some errors. More opportunities than would otherwise be the case to trade circuit depth for circuit width. And most importantly, it would be even faster than QISC at runtime, which just throws hardware at the problem trying to speed up everything. But one of the disadvantages could be too much classical logic, that if you're designing a circuit and if you're struggling on how do I do this quantumly, if it's possible to do it classically, some people, I could see some people falling back and ending up doing it classically instead of quantumly, and that just defeats the purpose of using a quantum computer and trying to do quantum computation. By definition, you cannot have quantum computational advantage for anything you're doing classically, even if you're doing it classically on a quantum computer. Also, the control systems have limits, although we'd have to imagine that will improve over time as the control system hardware gets better, as the memory is upgraded in them as well. But if you're playing with dynamic circuits and you're trying to do something, you've got delusions of grandeur and you're trying to do something really big, I'm guilty of that, you will hit control system limits at some point. Then coherence limits, and I hinted to this with qSync 2, that we initialize a qubit, we use it, we measure, we reset, and we reuse it again. And in principle, we need to maintain coherence from the time we start using the qubit until the next time we measure it. But every operation we do takes time. Every quantum operation takes time. And the slowest operation, to my knowledge, is the measurement. So if we have a mid-circuit measurement in particular, keep in mind that that's slow. But in addition to that, the conditional statements are also relatively slow. So we measure, we reset, we reuse, we're applying conditional logic, and we are eating into our available coherence time, which is why if I'm going to try to implement hundreds or thousands of conditional statements on real hardware, not only are the control systems going to say, no way, buddy, but the qubits are asleep long before that's finished. And also the example that I gave before of we have the qubit that's being acted on dynamically, and the other qubit that isn't, the one that needs the error suppression settings for the pass manager, that all of those, in addition to the mid-circuit measurements taking time, all of those conditional statements and the time they take are eating into the coherence times of the qubits that are not being acted on dynamically. So something to keep in mind as you're building your circuit, be aware of the qubits that are not being acted on dynamically, because all of these classical operations are actually the slowest operations that you're executing. Also, excuse me, in principle, like I just said, we measure, we reset, we reuse. In principle, we need to maintain coherence from that starting point when we start using the qubit again until the next time we measure that qubit. In principle. In practice, though, we initialize the qubit, we use it, we measure, reset, reuse, and that process is not perfect. So when we talk about quantum computers and we talk about noise and errors and nothing works perfectly just yet, we can't talk about dynamic circuits and think that this is the one thing that actually works perfectly. It does not. So while in principle, we're starting off with a clean qubit, in practice, not so much. Also, the composer, inside the IBM Quantum Portal, if you haven't taken a look, there are 3 ways to do quantum computing. There's the drag and drop circuit builder, the no code drag and drop circuit builder. There's the OpenQASM editor, and there is the IBM Quantum Lab with Jupyter notebooks. If you don't want to install Jupyter notebooks and Python on your laptop, then you can just go into the IBM Quantum Portal and it's all set up for you. But the composer currently supports OpenQASM 2 still, not OpenQASM 3. And that would be the better place to design your quantum circuits because you are limited to what can actually be implemented on the processor and next to the processor. I can easily imagine that you've got your Jupyter notebook and you've got some variables and you've got some classical processing going on, but it'd be very easy to do that locally. That processing and those variables are stored on your laptop, whereas for dynamic circuits, you need to make sure you're using the variables that are next to the processor where that information needs to be, and that your classical computation is happening next to the processor in order to get that speed up. And I could see that easily being a problem where the variables and the processing are happening in the wrong place. But again, if you use the composer, you would be constrained, if they implement this at some point, to designing your circuit. And this is what you have to work with. This is what's being done quantumly. And then you use your Jupyter notebook for your classical pre-processing and your classical post-processing. Also, I mentioned that IBM is not the only supporter of dynamic circuits. There are some others. Quantum machines, and I'll give a disclaimer that so far I have only had a presentation. I have not had a chance to use it hands-on. The package is called QA instead of Qiskit, QUA. And the main difference between QA and Qiskit is that QA is analog. So we're talking about dynamic pulse control, whereas what we've been looking at in this presentation is circuits, it's gates, and QA is an analog version of this. Now, in principle, IBM does support this. In principle, there are devices that both support dynamic circuits and support pulse control. But to my knowledge and having asked some questions, it has not been tested. So it either might work now or it might be supported in the future. But in principle, if you want to try dynamic pulse control with IBM, it might be possible. It also might not be. But either way, QA for analog has been doing it longer, which also, and again, with the disclaimer that by presentation only, it looks like Quantum Machines has been doing it for a little bit longer. So it looks like it might be more mature. There might be some more features that are implemented, again, with the disclaimer, but based on the presentation, it looks like it's been around a little bit longer. So much so that the dynamic VQE that I showed you before, which I came with before I had this presentation, they have a paper that you can see on screen, the address for a dynamic analog version of VQE. So not an original idea, unfortunately, but something you can take a look at and see that it's been around for a while and in use for, it seems to be a little bit longer. Then Quandela had a talk presentation recently, and they did not call it dynamic circuits, but in their description of some of the features that they'll be rolling out soon, they described functionality, excuse me, that functionally is dynamic circuits. And Quandela, if you're not familiar with them, is a photonics company. So we're talking about dynamic photonic quantum computation. And how would that look? I have no idea. If you look at how photonics works, how will that be done dynamically? No idea. But hopefully we'll see something within the next few months and be able to take a look at that. And also, we can't forget that the OpenQASM 3 specification has other contributors. So presumably there are other implementations of dynamic circuits if you want to try something else somewhere else. And the recurring theme is to check what the hardware supports, whatever hardware you're using, see what features have been implemented, what's being supported. But there are presumably other implementations of dynamic circuits out there. And with that, I will be happy to take any questions that anybody has.
Cool. Yeah, thanks, Brian. Pretty chill. Anyone got any questions? Yep, Timothy Stackman got a
Hi.
question.
Yes. So that slide where you had the circuit diagram of the variational quantum eigensolver, I noticed you had one part was just this box that said efficient SU2. Could you explain to me what's in that box?
Yes, so with VQE, you start off with a quantum circuit, and there are parameters, and the parameters are the angles of rotation, what we're doing to the qubits, those are variables. And the efficient SU2 is a function for creating that initial circuit with the parameters. And then it just looks differently. The other blocks are actually the same thing, but when we have the circuit diagram and we're implementing it conditionally, it just ends up looking differently. But anytime you see a box like that, that's just an existing function doing something. And in this case, that function is designing that initial circuit with the parameters. And then with the mid-circuit measurements, we're doing the computation, the classical computation to update those parameters, and then we're just implementing it again. So yeah, it's just a circuit with some rotations and some entanglement, but given a fancy name.
Okay, thanks.
But yeah, so that's the circuit. Dynamic VQE has two main parts. There's the quantum circuit part, which that is just a nondescript block representing that. And then the other part of it is a classical neural network, and the classical neural network is doing the parameter updates and is the relatively slow part of VQE. And then you put them together, and then you're able to calculate ground state energies and so forth.
Cool. There was another question, Brian, in the chat by Dev. You have talked about ChatGPT use. He wants you to explain it once again. How can we use ChatGPT platform to make quantum circuits?
Well, the easiest test is you can ask ChatGPT, how do I entangle or how do I well, I guess if you just ask it about entanglement, it should hopefully be able to figure out how to do that. But you can ask it a question about a very simple circuit. And I've done that with OpenQASM too, and it's definitely good code that comes out. But you can just ask it, how do I do this? With the disclaimer that it doesn't always work, but sometimes it does, and sometimes it's actually quite good. But you can just ask it, how do I implement this feature? And or even troubleshooting code. If it gives you code that generates an error, you take the error, you give it right back to it, and it'll give you new code, and then you can try that out. So if it doesn't work on the first try, it might not work ever. Sometimes it corrects itself, but yeah, you just ask it a question: how do I do this? And even it gives you, let's say, Python. You ask for it in Python, and then some quantum computing is switching to Julia. You can just ask it, hey, can you give me this in Julia instead? And you can do it conversationally like that. You just ask it a question, and it'll convert it from one language to another. OpenQASM 2, well, how do I implement this in Qiskit? How do I implement this in Circ? And really, it's just like if you wanted to ask me a question, but you just type it out instead and see what ChatGPT comes up with. But it's not
point there,
perfect.
Brian. Yeah, like,
but I'm not perfect either, so we're even.
Definitely gets your mind thinking though. That's cool. Just utilizing some new tools that are out there. Interesting. Yeah, sorry. Anne had her hand. Anne had.
Yeah.
Anne.
I'm here. Thank you. Great presentation. I had a general quantum computing industry state-of-the-art question. You all may have followed earlier in the year Rigetti, that has been, of course, one of the leaders in this field, or early adopters at least, almost got delisted from its public listing because it couldn't maintain its stock share price. And other entities like D-Wave have also struggled since they went public, which has led to talk of a quantum computing winter, at least in terms of financial viability. I'm wondering if you have any thoughts. You may not, you may be, totally involved in the technical, but on the other hand, without financing, it ain't gonna happen.
I'm completely biased, actually. I'm trying to think of how to answer that I don't like to go negative in my articles or what I say. Negativity doesn't get very far, but I guess the positive spin I'll put on that, especially for superconducting qubits, IBM crushes everybody else. It's just, if you look at, how do I not go negative? If you go to Rigetti's website and they list the T1 times for their devices, they are a small fraction of what IBM offers on their free devices. So if I were to look at that, I can pay to use these qubits that only last a fraction as long, or IBM's T1 times are so much longer. It's a no-brainer to me anyway to use IBM instead, and not just Rigetti, but other, again, superconducting devices in general. IBM just absolutely crushes everybody else. But that's not the only type of qubit out there. So there are other qubits. I guess I already did mention Quandela. Photonics works a little bit differently. So you still have to ask the question, what can I do different photonically that I can't necessarily do with IBM? Or what can I do with neutral atoms that's very different actually from superconducting qubits? So quantum dots are not available yet, but hopefully soon. So with these other qubit types, what can we maybe do with them that gives us an advantage over a different qubit type? And that is definitely an open question. And I'm saying that from playing with as many qubit types as I possibly can. But your question was kind of investment related. There are still other companies that are still doing very interesting things, but yeah, I guess to be totally honest, if another company came out and said, we're going to start doing something with superconducting, I would say, why? Why would you challenge IBM, which is so far ahead? Because they really spend a ton of money on it, But now these other things that IBM isn't doing, photonics, atoms, neutral atoms, and what did I say before, quantum dots, they're very different in how you use them, and maybe there's stuff we can do with them a little bit differently. So there's still reason to look into those. And then even different software platforms, different tools, different frameworks, different things with different advantages and disadvantages. So still things to look into, but it would be hard to say. And I'd say some of the industry does this where they say, well, if this one company has some bad news, that maybe that'll negatively reflect on the whole industry, but I don't think that should be the case. In any industry, you can have this one company and this company is not doing so well, but no, there's still plenty of other stuff out there. It's just where are you focusing your attention? Where are you investing your money? And you just want to invest it in the right places. I hope that answered your question.
Thank you, Brian. No, that's very helpful. I appreciate it.
Okay. Barry Bird has his hand up.
Yeah, hi. What you just said interests me. You say I'm going to do something differently if I'm using photonic than if I'm using superconducting or using neutral atoms. And from my point of view, I'm just always developing, just working with simple algorithms, just making sure that they work or making sure that they don't work, not worrying about performance. Is there anything I should be aware of at that very shallow level about the differences between the technologies? I'm coming at it just completely as computer science and math and not physics and not performance.
They all have more similarities than you might guess. A qubit is kind of a qubit is kind of a qubit, except that atoms are qubits. But there's an awful lot of similarity. There's a lot of difference in how you do it, but still a lot of overlap. But it's still an open question, I would say. What is the real difference, even on a small scale? What can I do with one thing better than another? Because you can kind of do everything everywhere, but it's just implemented differently. And then you also have what the qubits can probably do, and then the support for that qubit. We can do more maybe over here, but that's not really a testament to the qubit. That's just a testament to what's been implemented. But in principle, we could do it over here. So for example, photonics, I have not seen the equivalent of phases implemented anywhere. So you're kind of limited to what you can do with photonics, but at the same time, it's the most interesting qubit in my opinion, because it's photons. That doesn't really matter computationally what the qubit is. A qubit is a qubit is 2 states, a qubit is 3 states, and a qubit could be 2 or more states. So I should be using qubit, and in principle, they all work kind of the same. But then it could be, I guess, which is more intuitive, or which is the most interesting, or really whatever you're trying to do experimentally, who supports with both hardware and software what you're trying to do, I guess. I hope that answered your question.
Cool. Yeah, Bill had a question. Bill, he's in a noisy location. So since we have been talking about ChatGPT, what are your thoughts about the growing field of quantum natural language processing, and how do you think it could benefit things like ChatGPT?
I have not looked into QNLP that deeply, but I would see it having value generatively, because qSync, which I use as an example because I worked on it, we're composing music. It could easily be adapted to imagery. It could not saying QNLP is easy, but what I'm saying is the adaptation to being able to synthesize language. I could see it being adapted to that. And how it would work with interpreting other text, I haven't looked into it, but quantum is very it is probabilistic. So if we see the letters THE, it's probably the word the. You could never really say that the is the. It's just probably the to a great extent. And but yeah, there's a lot of research being done on that. I would say generatively, even without looking at it, it should be possible. And the other applications of it, well, there's some really, really smart people working on it. So I guess that's the best answer to that question.
Yeah, thanks for taking that, Brian. It's kind of out of field, but yeah. Yeah, Tim, sorry, you had another question?
Oh, Yes. Are you aware of any quantum machine learning for data in a graph format?
Um, Off the top of my head, I'm not thinking of anything. Yeah, off the top of my head, I'm drawing a blank.
Okay.
I'd say it's possible. There's so many papers out there. If you go to archive, maybe somebody's touched on that, but yeah, off the top of my head, unfortunately, I can't think of anything.
Okay, that's fine. That's fine. Yes, because yeah, what I'm working on now is learning machine learning for data in a graph format. And then for the job that I'll be working at, I'll probably want to start off doing that with classical computation, but then eventually move on to doing that using quantum computation.
And I'll make a point, since you're on the topic, that it all depends on your definition of quantum machine learning also, because quantum machine learning, like the dynamic VQE that I showed before, what's called quantum machine learning is typically a quantum circuit that actually has a classical neural network that's really doing the guts of it. Whereas I define quantum machine learning as the learning is being done quantumly. So, and I would call it either variational machine learning or hybrid machine learning, what everybody else calls QML, that the learning is being done classically. I would like to see it done quantumly in the circuit where the learning is being done, and then use that to optimize your graph. Otherwise, you kind of have you have a graph, and you still have a classical neural network actually doing the bulk of the work.
Okay.
Sorry, I'm just gonna hop in there. Yeah. Oh wait, did you have another point? I just wanted to keep the questions kind of like related to the presentation. I just had a
could
question.
talk about this all day. Yeah. So yeah, stop me.
Yeah, no,
Feel free to
I just had a quick question. So you were pretty much just saying. So I was wondering why you brought a Quandela in the presentation.
Because I'm a fan.
Okay, so you are, yeah.
Yeah, dynamic photonic circuits, I can't yet visualize what that would look like, but I use their Asila device. I've used it quite a bit. Yeah, I don't know that I've really tried to push it to its limits, but to see what can be done photonically, and then how would you do that dynamically? Because if you've used photonics, and my characterization, this is why physicists don't like me, but I'm going to use it anyway. So you've got the lasers, you're firing photons, and you kind of have these racetracks, or if you want to imagine it like the trench run at the end of the original Star Wars, you've got this trench that the photon is following, and then it hits a beam splitter. And then this is where it gets interesting, where the photon essentially decides, I either want to stay in my trench or I want to move over to the next trench. And with the angle of the rotation of the beam splitter, we can control the probability of where the photon is going to go, but still the photon decides. But then we have to, well, first of all, it's very, very fast. It's moving at the speed of light. And then it hits the detector, and then we need the information from that detector to do anything else. So that's why I'm curious. I don't know how we would do that dynamically, because then I guess you would have to detect the photons, then classically mid-process that, and then set up, which isn't super fast. They're speeding it up. but it's not super fast to then reconfigure basically the racetrack to rebuild the second Death Star and fire the next round of photons and see what detectors they hit, and then build, God forbid, whatever was in the sequel trilogy that Disney killed Star Wars. But anyway, so you hit the detectors, and then you have to reconfigure the photonic circuit and then fire a bunch of new photons. And my functions, not that it's relevant, but I call my functions aim photon, fire photon. Whether you want to go with Star Trek or Star Wars, it's just fun. And then you can play the music. And now I'm really off topic, but I literally play the Star Wars theme when I'm firing photons, because you can see when your job is actually running. So the photons are actually being emitted. Well, it's done too quickly, but it's fun is what I'm saying. And dynamic circuits are in the works. So much like dynamic VQE, fire the photons, they hit the detectors, have a new photonic circuit, do it again, new photonic circuit. So I guess you could do a dynamic photonic VQE, but not yet, but hopefully soon.
So does that mean that you're bullish on photonic and superconducting quantum computers?
Well, you can't do as much yet between Xanadu and Quandela. You can't do as many different operations on real hardware. Now, there are simulators where you can do quite a bit more, but on real hardware, you can't actually do that much yet. But it's definitely interesting, more interesting. And then the question is, with that different format, so we have a quantum circuit and we have these gate operations and we can do lots of stuff. But then with photonics, even though it would seem to be limited, we just have beam splitters that we can set to different angles. But can we do something differently with the way it's implemented compared to superconducting? I'm not even going to say superconducting, I'll say IBM, since I got onto that path earlier. Can we do something differently? What can we do differently? Open question. But well, no, I do have something really, really interesting that it's still in the early stages that might be something that photonics can do that IBM can't do. Maybe, but I haven't tested it yet.
Yeah,
If
so
you're
that actually
so-
kind of goes really well into the next question by Bo. He was just asking, in terms of superconducting quantum computers, can you compare IBM and Google?
Well, Google, to my knowledge, is not available, or at least it's not available to me. So that's where a lot of the announcements that are made, and you see this all this time, this company is doing this and this company is doing that, but you really need to use them and compare them side by side. So one example, I don't really want to talk negatively about anybody. I guess it's too late for that, but you really need to run it side by side. So as a user, some of the advantages of IBM is there are, how many devices now? Like 8, 9, 10 devices that anybody can use absolutely for free, as much as you could possibly want to use it. Only a few qubits, but you can really bang away at it. And then you can imagine, even if you haven't used larger devices, you'd have to imagine that the paid devices have to be at least the same quality or better. But then Google is an open question of, I just don't know. They publish research and there's peer review and a lot of scrutiny, but if you can't use it, you don't really know. Whereas, some of the other devices, you can use them. And again, for superconducting, I just circled back to IBM. More devices, more devices that are available 24/7. There's always something available, and no limit on, especially as someone learning. I'm just getting started and I'm playing with small circuits, I can run it as many times as I want. I can run it on the simulator first, but I can play with real qubits as much as I want. So that, I guess that doesn't really answer the question, but Google, I can't know without actually having access to it.
Yeah, just a quick question. The IBM Quantum Summit last year, I assume you went in person for that, right?
Yes.
Yeah, where was it?
It was in New York, off
Nice.
topic, but I was born in New York and I was freezing. So for anybody who missed that, I am now in the Philippines. I didn't realize how much I had acclimated to the weather here. I was freezing in New York the entire time, even though I was born there, absolutely freezing. But the Quantum Summit was in a fairly large room. I don't know what the attendance was. It looked like easily hundreds of people. The practitioners forum the next day, I believe, was 80 participants. It was a smaller group to really deep dive the previous day's announcements. But Quantum Summit, they announced like, what was it, 10 major announcements, something like that. And Osprey kind of stole the show, but they had a bunch of other announcements as well. And yeah, so that was in New York, and lots of familiar faces, familiar companies there.
Cool. Yeah, New York is always a great time. Yeah, I don't want to just. Did anyone have any last minute questions? It's 9 o'clock on a Saturday. I'm sure you would like to get out of your day. Actually, Rajiv just asked you any future summit you recommend for quantum computing this year.
Do I want to go off on a tirade on this one? A little bit. Well, being not to talk about the quality of the summit so much, but there's a lot of talk about accessibility and democratization and inclusivity and all that kind of stuff. But much of the world just can't afford to attend these things. To fly anywhere in the world with lesser developed economies, shall we say. So I like anything that's online for free and anybody can access it. Not just online because anybody can access it, but free. And it's one of the reasons why my books are free. Even a small amount can be incredibly cost prohibitive in much of the world. So these summits that cost a lot of money and you got to fly to them and so forth, it's excluding much of the world, even though so many people are talking about let's include everybody. So that's my personal bias, and that's probably because of my geography and where I am that I can see that I prefer any conference, not qualitatively, but based on its actual accessibility online for free. And also the ones where, and none in particular, where they're more informative in nature. There was one recently, I won't mention its name, but it was basically one giant marketing pitch. A marketing pitch after another, and to some extent that's going to happen, but there was nothing really. There were 2 sessions out of the whole conference that were really informative, and the rest of it was, yeah, let's just show you our product, which there's some value in, but then there are others that really are more informative generally, or informative about a product. Hey, I want to try that product out because of this presentation, but not too marketing pitchy.
True. Rajiv, also in the chat, someone did say IE Quantum Summit. Sounds chill. Probably check that out. But yeah, great.
IEEE?
Yeah, IEEE. Yeah, that's what they said. That's what David says.
Yeah, I attended one of those IEEE Quantum, so that was a mix of informative sessions and some marketing pitches as well. But there were at least a number of sessions that, you take out a notepad and some paper or digitally out or however you want to do it, and it's actually worth taking some notes and actually learning something from.
Cool. Yeah. Final round of questions, 9 o'clock. Don't want to keep everyone on a Saturday. Going once, going twice. Sold.
And
Cool,
greetings
yeah.
from the future, by the way, since it's Sunday where I am. It's been Sunday for a while.
Yeah, it is Sunday morning over there, but it is, 9 p.m. is early. True. Yeah, well, yeah, thanks everybody for joining. Brian, that was honestly that was a great presentation. Very strong recap of what came up in the newest version release of qSync and how you felt about dynamic quantum circuits. Yeah, any last words before we head off? Or
Yeah, it's much more fun to play with dynamic circuits than to listen to me talk about it. Just well, it's hard to not talk about IBM, but an IBM Quantum account is free. You don't have to install anything. You can use the simulator for free. You can use real qubits for free. You can try out dynamic circuits and play around with it. And then you can look at, if you want, the OpenQASM3 specification and see who else is doing it. I should probably do that myself at some point, but you can reach out to Quantum Machines at least, since if you prefer analog, if your background is more amenable to analog quantum computing, you can reach out to Quantum Machines. And if you want to know what dynamic photonics looks like when it comes out, reach out to Quandela, follow them. And I should probably see who else is doing it, so I'm not leaving anybody out. But yeah, use it. That's the most important thing. It's far more interesting than anything I can say. Yeah, just actually do it.
cool. Yeah, no, for sure. Guys, make sure to follow Brian on Medium. Follow his Quantum Zeitgeist on LinkedIn. Pretty good content there.
I do see popping up here, Quera. Not that you can do what we've been talking about at the moment, but Quera's roadmap, so that's neutral atoms. The roadmap includes a different kind of dynamic quantum computing, whereas you can arrange your array of neutral atoms and do something. But now the dynamic nature of that would be you can move the atoms around. So we can take these atoms here, move them over here, and just measure those. Or we can take these atoms and move these over here, and that's a kind of memory. We want to save these off to the side for later. So dynamic in the sense of, and this is where it gets, you can't, well, I guess you could do a ton of swaps with superconducting qubits, but a completely different dynamic of physically moving the atoms around and then doing something else, then physically move the atoms around and doing something else. So that is, I got to add that to a slide. Thank you very much. Actually, I should have thought about that, but that's on the roadmap for Quera, at least, to do dynamic atomic computing.
Great. Cool. Yeah, thanks, David. Yeah, Brian, well, thanks for joining us today. Great presentation, great topic. Thanks everyone for joining as well on Saturday. Yeah, I guess we'll catch you all at the next one. And the next one's coming up March 28th, right, Helen? March 28th?
26th.
26th, yeah, March 26th.
Algorithm.
Shor's algorithm. So make sure to tune into that if people are available. And yeah, make sure you check out Brian's content. All the links are in the Meetup group page. Good content on there. And yeah, have a great rest of your Saturday evening / Sunday morning for Brian. Cool.
Thank you very much. And thank you all for showing up. It's a good size audience. Thank you. And the good number of questions. I really appreciate it. Thank you very much.
Good night, everybody. Peace.